Waiting for mortgage rates to drop could be a costly mistake. Once rates drop, new home buyers will enter the market and prices will soar even higher. At Churchill Mortgage, you can get a free analysis and learn how to avoid the trap of waiting for interest rates to drop. Buy now and refi later at churchillmortgage.com. This is a paid advertisement. NMLS ID 1591. NMLS ConsumerAccess.org. Equal Housing Lender. 1749 Mallory Lane, Suite 100, Brentwood, Tennessee 37027.
Experiences are what people love the most about travel. That's why they love Viator. They have over 300,000 bookable experiences and something for everyone. Plus, their travel experiences have millions of real traveler reviews, so you have the information you need to book the best activities for your trip. Download the Viator app now and use code Viator10 for 10% off your first booking in the app. One app, over 300,000 travel experiences you'll remember. Do more with Viator.
Hi there, Andrew Dunkley here, the host of Space Nuts, and good to be with you for another episode 371. Coming up on this week's episode, could it be Planet 9, Planet 9.5, or something else? It looks like there may be a planet out there in the Kuiper Belt, and round about Earth-size, perhaps, which is fascinating. But not Planet 9, possibly. Maybe Planet 9.5. We're going to talk about that. And the James Webb Space Telescope has observed the closest supernova of the modern era. That is a fascinating discovery as well. We'll also be talking comets, space-time, betting on Big Bangs and antimatter, and a few other things in our question and answer session later on. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me to talk about all of that, minus the dad jokes, we hope, is Professor Fred Watson, astronomer at large. Hello, Fred.
Where do you get your where do planets get their where do planets get their music from?
I don't know.
Neptunes.
Oh, I should have known that. I should have known. That's almost as horrible as the one you told on the TikTok.
TikTok, yeah, sorry. That was the second one. And I can't even tell either of them without jumbling up the words. I think I'm the world's worst dad joke teller. And you at least always get the words in the right order.
Oh, gosh. I'm not going to do one. I'm not going to do one. I so want to, though. What do you call a telescope that can't stop running itself? See, I blew it now. I've caught it from you. What do you call a telescope that can't stop running into stuff?
Pretty dod telescope, really.
A kaleidoscope.
Oh,
horrible. So I knew I could do worse.
That's good.
I knew I could do worse.
It's a good one.
Okay. With all that in mind and the remnants of our audience, let's get down to business. Now, this one really excites me because we have talked about Planet 9 and the search continues. But this is a story about a discovery that probably is not Planet 9, but it is a yet-to-be-confirmed potential maybe planet in the Kuiper Belt, which is suggested to be possibly Earth-like. So it could be a planet rather than a planetoid, Fred.
Well, yes, that's right. And that's a very good point on which to introduce this, because planetoids, I suppose we call dwarf planets planetoids now.
I just like planetoid. It sounds like a good word.
Complaint, though, doesn't it? It's a bit
no,
like
it doesn't.
Meteoroid. The key thing that we're talking about really is, as you said, the Kuiper Belt, way out there, beyond the orbit of Neptune, and in fact, we think Pluto is a particularly large Kuiper Belt object. Not the largest. There's one that's actually about the same diameter, but greater in mass. I'm trying to remember which one it is. It'll come back to me.
Sedna?
No, it's not Sedna. It's the its moon is called Dysnomia. So what's it called? I've forgotten the name of it. That's ridiculous. Anyway, it doesn't matter because the bottom line is that these things range in size from probably a couple of 100 kilometers, because below that it's not going to be a dwarf planet because it won't have enough gravity to pull it into a spherical shape. So dwarf planets are defined as being big enough that gravity's pulled them into a spherical or near spherical shape. Sedna, Koeo, there's a whole heap of them that are that sort of shape and therefore classified as dwarf planets. In order to be promoted to planet status, though, you've got to get rid of all the other ones. You've got to have cleared your bit of the solar system of other debris.
Oh, okay. So if you're living in rubbish, you don't get the Guernsey.
No, that's right. You essentially the debris left over from whatever formed you as a dwarf planet. If that's still around, well, you're not a planet.
Even the solar system has a ghetto.
Yeah, it's got class structure, really, hasn't it?
It does. Yeah,
right.
If you're out there in the cold, get a job.
Get a job. Yes, wasn't that some famous Australian federal politician?
Yes, it was. It was.
Or get a job. Anyway, yes, so sympathetic. Enough of that. This is a study that has come from, two Japanese institutions, the National Astronomical Observatory of Japan, NAOJ, which I visited probably a couple of decades ago, and Kindai University. And what they've done, the scientists who are at these institutions who are interested in this work, and this is being published in the Astronomical Journal, which is one of the world's leading journals on astronomy, they have looked at the objects in the Kuiper Belt, of which we know of more than 1,000, and looked at their orbits, studied the way their orbits are distributed, and things like the alignment of their what they call the major axis, that's the long axis of an elliptical orbit, and essentially studied these objects, and some of them are probably not much more than asteroids, and see that there is a kind of circulation among them, in that some of their motions are not as random as you might think they ought to be. And that is suggesting to these authors that, yes, somewhere lurking inside the Kuiper Belt itself, which is, as I said, it's where Pluto is, it's just beyond the orbit of Neptune, they think there is a planet there whose gravity is shepherding these objects to behave in certain ways. Okay. Now, that is a very similar story to the Planet 9 story.
It is.
But the Planet 9 story is different in that what you're looking at there is not objects in the Kuiper Belt, which is the sort of nearest of the disks of outer asteroids beyond the orbit of Neptune. What the Planet 9 story is looking at is what are called ETNOs, Extreme Trans-Neptunian Objects. These are things that are way, way beyond the orbit of Neptune. Remembering that Neptune is about 30 times the distance from the Sun as we are on Earth, what's called an astronomical unit.
Yeah.
So the Planet 9 story is looking at something that's probably more than 1,000 astronomical units from the Sun, whereas the Kuiper Belt story, this new suspected solar system planet story, is about an object that's probably about half that distance from the Sun, maybe something like 500 astronomical units, but still near enough to the Kuiper Belt for its gravity to have a significant pull on these objects. And of course, this the idea of discovering something because of its gravitational influence on something else is an old idea. That's how the planet Neptune was discovered back in 1846 by people looking at the way the orbit of Uranus behaved. Uranus had what we call gravitational perturbations in it. In other words, it was being nudged by gravity in a way that couldn't be accounted for by the other 7 planets. So the orbit of Neptune is what was found. Sorry, that couldn't be accounted for by the other 6 planets because Uranus was the 7th, and then Neptune, the 8th planet, was found as a result of that. So, the idea of using planetary what you might call, transgressions from normal motion of planets, that is a great way to find other objects. And so that's what these authors are now proposing, that maybe there is a trans-Neptunian planet that we haven't yet discovered.
Okay. Now, as you say, if it's sort of living in a rubble pile, and they confirm the discovery and goes through the motions, and it gains some kind of status, whether it's a planet or a dwarf planet or an object of some significance in the Kuiper Belt, will be determined by whether or not it's swept its doorstep.
Yes, that's exactly right. As to how it's defined. Yes, you're quite.
So if it's in an orbit where it's basically spread the debris away and don't come near me, this is my space.
Yep.
Rack off. It could well be a planet.
Yeah, that's
fully-fledged planet.
If it's big enough to be spherical for its own gravity to have pulled it into a spherical shape, then it will be a planet. As you said, if it swept its own doorstep. I do love that term, Andrew.
Thank you.
You should be on the radio.
I'll think about it.
Yeah. So if it's done that, that's fine. It's counted as a planet. And wouldn't that be amazing if the planet 9 that is finally discovered or recognised turns out not to be the one that we've all been talking about for the last 8 years, I think, 7 years now.
It would not surprise me. No, because we've been so intent on Planet 9, and other people are looking somewhere else and going, well, hang on a minute. I think we've found a 9th one that, will put Planet 9 out to pasture for a while, and we'll have to change that to Planet 10 if this all comes to fruition.
It could be. Wouldn't that be a turn up for the books if the other one turned out to be Planet 10?
Yeah.
So, and what's being suggested here, whereas if I remember rightly, Planet 9 is thought to be at least 4 times the mass of the Earth. We're talking about something smaller with this, I don't know what we should call it, Planet 9A or something like that.
Yeah, I'm not sure yet. What they're saying, it's a bit bigger than Earth, possibly.
Yeah, 1.5 to 3 times the size of Earth.
Wow.
And something else that you would think this might make it easier to find, because it's thought to be tilted. Its orbit is thought to be tilted at an inclination of about 30 degrees. Now, that's a significant tilt of the orbit of a planet, and might suggest that actually it's going to turn out to be not a planet but a dwarf planet, because all the planets lie much closer to the ecliptic, the plane of the Earth's orbit, than that. I think Mercury's got the highest tilt. I can't remember what it is, but it's the highest of all the planets. It's in the region of 5 to 10 degrees.
Okay.
We're talking here about something tilted, whose orbit is tilted at about 30 degrees to the plane of the ecliptic. And that might make it easier to see as well, because you're looking outside the disk of debris that is where the asteroids are and where, a lot of the Kuiper Belt objects are.
Yeah, but if it's outside of that, doesn't that lean more towards it being a planet rather than a dwarf planet or a
Yes,
piece
it does.
of rubble?
It would be exactly what you've said. It wouldn't be the tilt of the orbit that would define it or distinguish whether it was a planet or a dwarf planet. It will be that point that you made before, that it's swept up all the other debris in its orbital neighborhood. Okay. Either by accretion, that means things crashing into it, or by gravitationally kicking them out, or actually, as in the case of Jupiter and actually some of the other planets as well, by herding all these other objects into a point ahead of or behind the planet in its orbit, which is what we call the Trojan asteroids. In Jupiter's case, there's thousands of them. Some of them ahead of Jupiter, 60 degrees ahead of Jupiter, some 60 degrees behind Jupiter in the two stable Lagrange points.
I read the other day that Jupiter got hit and an amateur astronomer actually video recorded it.
That happens from time to time. That's interesting. I haven't picked up on this one. This is a recent one then, is it?
Yeah, it was only the other day.
Okay.
But yeah, nice pickup by the amateur astronomer, and it's been confirmed by other astronomical observations. So, it definitely happened. They got the flash of the impact.
Yes. So, there've been a few such observations made, probably, one every 3 or 4 years, we get an amateur who spotted something hitting Jupiter. It's a great thing. And of course, it's very much the province of the amateur community. The fact that you can look at Jupiter, if you want to, you can look at Jupiter every night. It's just like Trevor Barry, who apparently was featured on the telly last night, out there in Broken Hill. He observes Saturn every night. And so when anything's going on Saturn, Trevor's going to know about it. And he's got connections in very high places in NASA. So he can feed that to anybody who wants to follow up, for example, with the Hubble telescope.
I believe he picked up a major award recently.
He did.
Yeah. That's right.
He had one last year, a national award. This year he got an international award.
So just to wrap up the potential ninth planet theory, how do they confirm it or deny it?
So I think the first thing that has to happen is more observations of the Kuiper Belt objects themselves, to refine their orbits, to gather as much data as you can on as many objects as you can, to be able to refine your hypothesis about what gravity it is that they're feeling that is not yet accounted for in the solar system. And then once you can, I suppose, narrow down the target area of where you think this object might be, certainly in terms of its direction from the Earth, then you can start looking, as has happened in the case of Planet 9, by big telescopes looking for a slowly moving object way out there in the depths of the solar system. That's the thing that makes these things so hard to find. The further away you go from the sun, the more slowly the thing appears to move through the sky, partly because it's physically moving more slowly, but also there's the distance effect. Yeah. It takes a lot longer for it to cover the same angle across the sky.
Yeah, like observing the guideposts on the side of the road flashing by, and then you look at the mountains and they don't appear to be moving much at all.
That's right.
Oh, gee, I'm on a roll today.
Yeah, as I said, you should be on the radio.
Okay, well, this is one we'll keep an eye on, because there might be more on this if they can confirm those observations or those theories, and maybe it's a ninth planet out there somewhere near the Kuiper Belt, which would be really exciting. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson. Let's just take a quick break from the show to tell you about our sponsor, Incogni. Now, I have spoken to you about them a couple of episodes back. This is a really interesting idea, one that I applaud, actually, because there's a lot of information out there in the ether, on the internet, personal information, probably personal information of yours that is being used for illicit purposes, whether it's to, send you spam or get your phone number so they can spam you on the phone, or to, being collected by those overseas organisations in teleconferencing rooms to try and convince you to spend money on something that doesn't exist. There's all that sort of stuff going on. A lot of this information ends up on the dark web, and it is sold, it is traded like a commodity so that they can dupe you into spending money for something that doesn't exist or is false or whatever. Well, Incogni is an organisation that has decided to do something about it. And I'll quote from their website: "Our mission is to help you take back control of your data privacy." And they're aiming to basically make life difficult for hackers, for people who invade your privacy, or those people that duplicate your profiles and pretend to be you. There's just so many nasty things going on online. So how do you stop it? Well, you could go in and try and fix it yourself. It would take you a couple of years and you'd have to keep doing it over and over again. Or you can get someone to do it for you. And that's where Incogni comes in. Incogni.com/spacenuts is the URL to go to, and have a look at what they can do. They are quite amazing, and they do this on your behalf. It's not expensive, but it basically enables you to clear all these nasty little spaces online of your data. And I'm sure a lot of people would welcome that. So if you're interested in finding out about Incogni, go to the special URL for a special price, incogni.com/spacenuts. That's incogni.com/spacenuts. And select one of their plans. They've got a 30-day money-back guarantee. Everything's encrypted. And look, it might just be the next big thing on the internet, and just for once, it benefits the honest user. So go and check it out for yourself today, incogni.com/spacenuts. Now back to the show.
0G, and I feel fine.
Space Nuts.
Now, Fred, we have been talking incessantly, regularly, about the discoveries and observations of the James Webb Space Telescope. And here we go again, the supposed closest supernova seen in the modern era has been I'm going to say discovered, but it's now been looked at by James Webb, which is a good tool for it.
It is. That's right. Absolutely. Certainly the biggest space telescope that we have, tuned to the infrared spectrum, and doing a very fine job. And you would expect that it wouldn't be long before the James Webb would turn its 18 segment mirror onto the, as you said, the brightest supernova in recent times, or the nearest supernova in recent times, supernova 1987A. Called that because it was the first one to be discovered in 1987 and was nearly discovered by a good friend and colleague of mine, Rob McNaught, who at that time worked in the telescope next to me on Siding Spring Mountain. I was working at the Schmidt telescope. He was working at an instrument called the Satellite Tracking Telescope, but he was using it to look for anything that was interesting. And he missed capturing the supernova at its first brightness, or peak of brightness, back in February 1987. So where is this supernova? It is a star in the Large Magellanic Cloud, visible from the southern hemisphere, which exploded, as I said, February 1987, except that the light had taken 168,000 years to get
to say.
Yeah, because that's its distance. So, and a naked eye supernova, I mean, I remember it. It was in some ways the most exciting thing that could have happened in modern astronomy, to have a naked eye supernova in the southern hemisphere with a very, very fine 4-meter class telescope all set to look at it, the Anglo-Australian telescope, which I was working at then, of course, as astronomer in charge. Sorry, I wasn't. That was a decade later, 1987. I was still working at the Schmidt telescope, the smaller telescope on Siding Spring Mountain. Anyway, it was very exciting. What they did at the Anglo-Australian telescope was they put together what was called a wooden spectrograph, a device made out of wood, which was used to get really high dispersion spectra, the rainbow colours with all that barcode of detail in them, that you could do because this was such a bright object. It was visible to the naked eye. And so what you could do was spread its light out a long way and look at the incredible detail in the spectrum by doing that. And it turned out that the telescope didn't have a spectrograph capable of doing that because they didn't expect the telescope to look at things as bright as this. But an event like Supernova 1987A was one not to be wasted. And many reputations were made in that era when people used this cobbled together spectrograph to look really into the incredible detail of the supernova and its remnants, what happened, to try and learn about the physics of the thing. So that's the backstory. Now what we have is a new facility, unhampered by bits of wood, and actually able to study.
Wouldn't you know it?
Wouldn't you know it? That's right.
I wouldn't. You would.
Okay, are we finished now?
I wouldn't go there again.
There must be more than that. I'm just going to draw a plank underneath this. Rubbish.
No, you're not. No, that's not bad.
Not bad. Anyway, there's a branch of the science that actually lets you... It's the best I can do, Andrew.
That's okay.
A branch of the science that lets you look into the innermost details of supernova remnants when you've got one as near as this, 168,000 light years. Yes, another galaxy, not our own Milky Way, but certainly the nearest supernova we've had the opportunity to study in detail. With a caveat that I'll come back to in a minute. Anyway, the Webb telescope has looked and produced a very, very fine image with the mid-infrared camera, if I remember rightly. which essentially probes the remnants of this explosion. Now, 35 years ago or thereabouts. Yep, 35 years ago, a little bit more.
That discovery was 23rd of February. We were married the 20th of January that year. So
there you go.
After we were married.
Cosmic event to celebrate your marriage.
Yeah, maybe.
You should try that out on Judy sometime. Just do you know that the heavens aligned for... Anyway, enough of that. What we can do now is look at the structure that is there, and you can see, really interesting bits like the fact that a shock wave that rippled out from the explosion itself actually had something to ripple through, because this star had been shedding its outer layers for decades before, maybe even hundreds of years before. It had been leaking its outer atmosphere into space. And then the explosion happened when it went supernova. And so that the shock wave spreads through that region of space that's rich in gas that has already been shed by the star, and you've got all this structure. There's we think that the sort of blob of gas that is around the supernova is shaped like an hourglass, with all the really interesting action taking place along the waist of the hourglass. I
can see what you're talking about now.
Yeah.
I wondered why it looked like a figure eight type.
Figure eight, yes,
scenario.
that's right. So we see it as a figure eight, but in 3 dimensions, it's probably an hourglass.
Yeah.
And the what's called the equatorial ring is where this shockwave is hitting the stuff around it, and there are hot spots around the ring. It's amazing. It's a string of pearls effect almost.
It is too. Yeah,
looking really quite remarkable. So a lot of structure. It's worthwhile, anybody who's interested in this, chasing up. There are a number of websites that have this image on them, including James Webb Telescope, but Universe Today is another one. Fraser Cain's website there, great stuff. And so we've got this wonderful new image with lots of detail in it. What I was going to say was following up on the websites is good, because it will give you a kind of almost a guided tour of the structure around this supernova remnant, so you can see what's going on. And we've got all these stars around it, which have got funny six petaled artifacts around them. And that, of course, that's the remnants of the diffraction spikes, which come from the fact that the mirrors are all hexagonal.
Wow.
In that hexagonal.
What a fascinating effect.
Yeah, it's lovely, isn't it?
It is. I wondered why they looked like that. I thought they were just blurred because they were in the background and they were using an iPhone.
Well, big iPhone. So yes, they almost look like Christmas decorations.
They do,
and they're highly processed, of course, in terms of the data processing to get the imagery out. So yeah, it's remarkable that we have a facility like the Webb to look at the remnants and study the light from this supernova. And the point I was going to, what I alluded to a few minutes ago, that the last bright supernova was, if I remember, Kepler's supernova, which I think was in 1604 or thereabouts. Again, a star within our own galaxy exploded. The one before that was Tycho Brahe's supernova in 1572. Again, a naked eye supernova, one that could be seen in daylight, and I think Kepler's could as well. And the thing that I think is fascinating, and I think it's true for both of these, and certainly other supernovae as well, we can still study the light of the explosion from those because of what are called light echoes. So you imagine an exploding star. It sends out a pulse of light that doesn't last very long. It only lasts a month or so. But as it goes outwards from the site of the explosion, it hits distant clouds of dust, which light up. And that light is then scattered, some of it, back to Earth. So with modern telescopes, you can actually observe the pulse of light that came from a supernova within its first few months back in the 17th century, but look at it with the modern equipment that we would look at it with today. because of these light echoes. You see, the dust clouds light up with the light of the supernova explosion.
Fantastic.
Yeah, it's fantastic stuff.
Would you be able to observe, I know this is James Webb, so it's infrared, but would you be able to observe that after effects today with a backyard telescope at all?
You can, yes, there are, amateur astronomers who have imaged the supernova remnant of supernova 1987A, except that you don't get anything like the same detail because even though backyard telescopes are actually quite sensitive with modern detectors, what they don't have is what we in the trade call the plate scale, which is effectively the magnification. To get the magnification that you've got here, you need a 6.5 meter diameter telescope. And there aren't many amateurs who've got anything like that. And certainly if you have it on the ground, you're going to have blurring by the atmosphere. Yeah. The fact that the Webb is 6.5 meters in diameter and above the Earth's atmosphere is really what gets it into the details that we can see. Just one final comment. What we can't see is the remnant of the star supernova itself. We can't see the neutron star that's probably at the middle of all this because there's just too much dust and debris around to penetrate that, even for a telescope as powerful as the James Webb.
That'll all clear up eventually, won't it?
Yeah, it will in a few thousand years' time, and then whatever Webb's successor is in those days, they'll get a great view.
No, they'll probably be able to just go there by then.
Maybe even go there. That's right.
Don't know. All right. Fascinating story. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, time to tackle some questions and maybe even answer one. We've got a whole bunch of stuff today, kind of remnant text questions that I've sort of had on the back burner for no other reason than I never got around to them. But a quick question from Travis in New Zealand that you could answer rather quickly, I imagine. If a comet was coming our way and we had time to try to save the world, would it be possible to blast it with a laser and melt it?
Theoretically, it would if you had a big enough laser. But that's the problem. If you've got a comet that survived, its passage around the sun, and it's still made of solid lumps of ice or a solid lump of ice, you've got a lot of melting to do.
Yes.
And so I think the answer is, in practical terms, no. But theoretically, if you could mount enough radiation, yes, you could.
Wouldn't it keep refreezing, though?
It would. What would happen? It would probably. So as you melted it, it would essentially vaporize. It doesn't melt. It just it sublimes is the word. So it turns into vapor. So it would just, all the ice would get trailed out behind it, or maybe even in the direction of the laser. Actually, it would be an interesting phenomenon. Yeah. But you need a laser that's far more powerful than anything we have at the moment. But yeah, nice idea though.
Indeed. And I bet Travis's idea is going to be redundant when we invent the tractor beam and you drag them away.
There are such things already, but they're
not that powerful.
On molecular scales, that's right.
Exactly. Thanks, Travis. Duncan from Weymouth, who's been a regular sender-innerer of questions, usually audio questions, sent in a quick text question for Professor Fred. Are you coming back to the UK? Do you do talks anywhere, specifically around his area of the southwest, or is he always in Scotland? Well, yeah, he's always in Scotland. He'd love to be able to attend a talk and ask some questions in person, but he can't travel far because he's disabled. But sitting down in a pub with a beer with a good question-answer session would be his idea of great fun. Just wondering when you'll ever go back. You used to do science in the pub in Australia every year. They used to do science in the pub, and
Barbara, they'll do it again.
Exactly the same thing. The Q&A session with the audience.
That's right. Now, what's interesting is in about 2 weeks' time, I'll be going through Weymouth, I think.
Oh, wow.
I'm not actually sure exactly what our route will be, but we're certainly going to be in southwestern England. If we've got an email address for Duncan,
I do have. I can give it to you.
Pass it on to me, and I'll drop him a line. But by the time this episode goes to air, I think we'll have gone through that way.
Yes, because we are we're almost certainly working ahead to cover your trip, basically.
I don't know that there are any public talks on the horizon, but I will talk to Marnie. I mean, what is far more interesting than hearing from me is my colleague Dame Jocelyn Bell-Burnell, who will be with us on this trip, and with us. Actually, she won't be with us in Devon and Cornwall. No, she joins us in Wales. So, so it'll be just me, I'm afraid. But let me look at the itinerary just in case.
Yeah. Okay. Well, that's a good idea. And guess what? Just sent you the email with his email.
Thank you very much. Thank you, Andrew.
It's all right. So, Duncan, by the time you hear this, you may have heard from Fred. We'll see how you go with that. Let us know. Next question is from Robert in Norway. Hello, Fred and Andrew. Greetings from Norway. Just finished the back catalogue of the show and can't wait for more. That's a pity because we've finished. I wanted to ask, can we pretend that all of space and time is a flowing river, where the Big Bang could be the bottom of a waterfall, space would be the water itself, and time would be the flow, taking all sorts of weird detours because of rocks, etc., and ice, etc., all that stuff. If time stopped, could the universe be called frozen since nothing is happening, like the river would if given the cold in the coldness of space? Would be really cool if either of you wanted to meditate on this weird question and maybe add to the metaphor. Never stop the show. We're trying not to, Robert. Just depends on the time itself as to whether or not that continues. But for the foreseeable future, we're still around. I like his theory. Yeah, that's clever. Is he on the money?
Yeah, actually, he's using exactly the same term that we use. We call the expansion of the universe the Hubble flow. And
of course,
the Hubble flow is because the expansion was discovered by Edwin Hubble. Often we talk about the what we call the peculiar motions of galaxies. That means a motion of a galaxy that's peculiar to itself rather than its participation in the expansion of the universe or the Hubble flow. And we do imagine it as a river, that the peculiar velocity is like somebody in a boat that's zooming around on a river that is actually flowing and taking them along. They can move around independently in the boat, but they're still being carried along by the Hubble flow. And so that's precisely what we think of in terms of the expanding universe. Stopping time, which is a terrific idea, but we haven't really managed to work out how that might happen, would indeed freeze the Hubble flow, because if time stopped, everything stops. Yeah. And I think where Robert's coming from, and he'll be familiar with this, as you know, Andrew, Marnie and I have spent a long time, from time to time, touring around Norway in the middle of winter. And one thing you see, and they're beautiful, you'd be driving along a road, perhaps along a hillside, and there's right next to you is a frozen waterfall, which is water that would be normally flowing down, perhaps to go under a bridge under the road or something like that. And it's just solidified. It is a frozen waterfall, and they are absolutely spectacular. Because you've got lots and lots of ice, but it's just not moving. It's frozen in time. So that would be what the Hubble flow would look like if you stopped time. But but it's a great analogy, and Robert's right on the money with that.
There you go, Robert. Well done. We've got one from Nan, who refers to herself as AstroGirl70, and she just wanted to make a comment. Imagine my surprise when you answered my question on gravity on episode 345. Thank you so much. Fred's explanation was easy for this 79-year-old space nut to understand. I'm a big fan. Keep up the good work. I look forward to each episode. Thank you, Nan. That's lovely.
Yeah. Great from you, Nan.
And you know what? It confirms one thing I wasn't sure of, but you do have one fan. Now, we've got one from Kevin in Melbourne. Hi, guys. Love the show. It makes my Thursday exercise that much more enjoyable each week. I'm glad, because I don't exercise. I just sort of watch other people, and that's enough to get my heart going. So I'd like to place 2 bets out there, like some of the famous bets in history. Bet 1, I bet that what we think of as the Big Bang that started our universe was in fact the other side of a collapsed black hole, and that we are expanding towards the event horizon, which one day we will reach. That's bet 1. Bet 2, that all the missing antimatter will be found inside our protons. Recent evidence is suggesting that a lot more is going on inside the old proton than previously thought, and I'm betting we find an equal amount of antimatter involved in holding them together. So I'm 52, so I reckon I've got about 30 years left in which these discoveries will be made. Anyone want to take my dollar?
Yeah, I'll take him on.
I knew you would. Knew you would.
Yeah, because I think I'd bet the other way, actually.
Well, that's interesting, isn't it? So
on both counts.
So we're not on the other side of collapsed black hole and heading for the event horizon.
Yeah, I mean that's effectively old Roger Penrose's idea that our big bangs come from black holes. I don't think anybody believes him, but he's got no way of proving it one way or the other at the moment. We need more observations, and it'll probably be observations of the cosmic microwave background radiation that give us the answer.
Okay. And the second bet was antimatter will be found in protons.
Yeah. Who knows? It's certainly true that protons are turning out to be more complicated than we thought they were. They're made of quarks and things. They're not fundamental particles, unlike electrons and neutrinos and stuff of that sort, which are photons. So, yeah, I don't think that's likely either.
Okay. Bad luck. Hold on to your money, Kev.
Well, I'm putting my dollar there as well.
All right. Well, we'll put the $2 on a table and we'll wait until the answers are known.
2 years.
Yeah. With inflation, you could end up with a fair stash of cash anyway, judging by how long this might take.
Yes.
We'll put it in a bank account with interest and see what happens. Thanks, Kev. Now, this is a question that we've been sort of pondering for a while from Rusty in Donnybrook. He sent us graphs and background information. He's basically dredging up that old light issue where, how is it we can still see light if it's already past us? And, why do we know what we know about light when it's all gone post Big Bang? And he sent us a lot of information, a lot of calculations, a lot of graphs, very pretty graphs. And he's still pondering the question, Fred. We just can't dismiss some people in regard to all this leftover light.
No, we would never do that.
No, I don't want to. They keep thinking about it, and light keeps coming up. Keeps coming up in the Q&A sessions.
It does, yeah. So I'm not really answering Rusty's questions directly here, but we'll need to look a little bit more detail at what he's sent us. But I just wanted to clarify that, that apparent conundrum, hasn't the light from the early universe gone past us already? And I think it's because of a misunderstanding as to particularly what the cosmic microwave background radiation is. And that's the flash of the Big Bang, which we can still see. And the best analogue that, to me, always makes this seem crystal clear, and I hope it will to everybody else, is...
Mostly Rusty.
Yeah. Well, anybody who's interested. It's the cheering audience analogy. So if you imagine that you're at a concert of some sort, an outdoor concert, maybe with a huge band, Andrew Dunkley and the Perambulators or something like that, very famous band.
Andrew and the Zimmer Framers.
Yes, that's right. Yeah. There, and you've got an audience which is spread over an enormous field or paddock outdoors, and everybody's listening to music, they're raving about it. the band stops and the audience breaks into uncontrolled cheering. So everywhere in this paddock, people are cheering, they're cheering wildly and with utter enthusiasm. And the band, Dunkley and the perambulators, they like this for a while, but then they get fed up. And so they say, "That's enough, stop." And so everybody stops cheering at the same time. Throughout the whole paddock, they all stop cheering at the same time. Now, the question is, you are in the middle of this lot. Do you immediately hear silence? And the answer is...
no.
Exactly. Because, so 1 second after everybody stopped cheering, you're still getting the cheers from people who are
away,
330 meters away.
Yeah.
That's right. Isn't it? That's the length of time, the length sound travels in a second. And then after 2 seconds, it's 660 meters. There's still sound coming to you from those people. So you don't hear silence. But what you've got is this kind of expanding ring of what you might call a cheering front, where as you listen, you can still hear the cheering coming from this expanding ring, and it's expanding at the speed of sound. And that's an exact analogue of the cosmic microwave background radiation, because when the universe became transparent, which it did over a relatively short period, so the whole universe is glowing brightly. This is irrespective of the expansion. That folds in a bit later. Whole universe is glowing brightly, and then it stops glowing and becomes transparent. But because of the effect I've just mentioned, you don't immediately see darkness. What you see is a receding front of brightness that's going outwards at the speed of light, but you're still seeing the radiation that came from that. It's got a name. It's actually called the last scattering surface, because it's three-dimensional in the universe. That's the surface at which the last scattering of light took place in the Big Bang, and it's going away from us at the speed of light. And so we're in the middle of all this, and so the idea of light going past us doesn't actually come into it. It's what we can observe as a person stuck in the middle of an expanding a universe that has been brilliant everywhere, but that has stopped. And it stopped suddenly, but the fact that it stopped suddenly doesn't mean that you see darkness. You just see this radiation. And so the expansion of the universe is just something that you add to that, and all it does is redshifts the radiation from brilliant light into infrared, or in the case of ourselves, microwave radiation. So I think
instead of taking seconds in a crowd of cheering people that suddenly stop, it's taking
13.8 billion years. That's how far away it is now. That's that surface. So that perhaps puts a slightly different slant on where we are in the universe. We're not in the middle of things. We're only in the middle of our perception of the universe. The universe is full of light that's come from the Big Bang, but we see that front expanding at the speed of light. It's quite remarkable, really, when you think of it.
Well, that should keep Rusty quiet.
I don't think it will. I think Rusty will think around that, and he'll have another comment.
He'll send us more graphs.
That's fine.
I like the graphs.
Yeah.
So we didn't answer the question. We just pondered.
We put a different slant on it.
Yes. All right. Time for what round are we up to with Rusty's questions? I don't know, but keep them coming, Rusty. And if you'd like to send us some questions, you can do that too through our website, AMA tab, or send us your voice message on the right-hand side of our homepage. Have a look around while you're there. If you want to become a patron, you can do that. Or if you just want to go to the shop and buy something, you can do that too. Or you can just send us a message, whatever you like. Yes, but don't forget to tell us who you are and where you're from, so that we can tell everybody else. Because I don't know why. We just do. We like to know who you are. Yeah. But that just about wraps it up. Fred, thank you so much.
Pleasure, Andrew. Always good to talk.
And we'll catch you on the next episode. Indeed. I thought a dad joke was coming. I paused.
No,
there was room for one.
No.
Phew.
I'm out of
Okay. Thanks, Fred. We'll see you soon.
Cheers.
Fred Watson, astronomer at large, and thanks to Hugh in the studio who turned up today. He didn't do anything, but he was there. And from me, Andrew Dunkley, we look forward to your company on the very next episode of Space Nuts. See you then. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.